Hi everyone, my name is Noman Bashir and I am going to present my work on modeling the impact of snow on solar generation. Solar power is experiencing a very rapid, almost exponential growth. This figure shows that the added solar capacity for each year as well as the cumulative installed capacity. In 2019 alone, around 115 gigawatt of solar capacity was added to the grid. If this trend continues, solar PV will become the largest source of electricity by mid-century. And this trend is not unexpected. Solar PV has many benefits that the other forms of energy cannot offer. First, economics matter. Solar's cost is decreasing as the efficiency of cells increase and they are manufactured at large scale. In addition, it has low maintenance due to absence of moving parts. It does not require any fuel. And finally, it can be easily installed anywhere in the world. While increasing the solar capacity is desired, the key challenge to high penetration of solar is its variability. Solar is highly sensitive to environmental conditions and is mainly affected by clouds, temperature, and snow. Let's take a look at one side that we monitor. It produces high power when it is sunny and cold, slightly less power when sunny and hot, and highly variable power under clouds, and finally, very little power under snow. For solar to be viable, we have to solve this variability problem. And one way of doing that is to install large scale energy storage to store excess energy and supply energy when there is a solar deficit. While there is significant active research in energy storage, the current offerings remain too expensive for grid scale deployments and improvements in energy storage cost and efficiency are lagging improvements in solar. Now, without the storage, there is even a greater need to accurately model and predict sites' solar output. This can help make the day-to-day operation of the grid reliable. It is also crucial to the valuation of solar sites for financing and determining the year-round revenue from solar. We talked about solar modeling. Solar performance modeling estimates sites' current or future output based on sites' physical characteristics such as tilt, orientation, size, and weather conditions such as temperature and cloud. It is highly active research area and there are many open source models available such as PVLib and SAM from Department of Energy and Solar TK released by our lab. Once you calibrate these models for a given site, they are generally highly accurate, especially under clear skies. However, their accuracy significantly degrades in high latitude regions under snow, as these models either do not consider the effect of snow or use a very simple model that does not capture the complexity of snow effect. At this point, some of you may have a very natural thought in your head. Snow occurs only during winter, and not all places in the world get snow. Why should we care about modeling snow? We should care about modeling the effect of snow for two reasons. First, some regions with high solar growth, such as Massachusetts and Germany, get a lot of snow. Secondly, the effect of snow not only complicates grid operation in winter, but also heavily degrades the accuracy of year-round energy estimates. Both are very important for grid operation and financial analysis of sites. Here are some stats from one site that we monitor in Massachusetts. Remember that 2018 was very snowy in Massachusetts and 2019 did not get a lot of snow. We recorded a monthly solar output in March 2018 of 256 kilowatt hour and in March 2019 of 774 kilowatt hour. This 300% increase in monthly solar output was due almost exclusively to snow cover. Importantly, at this site, the difference in the solar output in winter months from January to March in 2018 and 2019 accounted for 65% of the difference in output over the whole year, even though the winter months only accounted for 8% of the yearly output in 2018. So the variability is primarily due to snow. And when I started working on this problem, I looked at the initial literature and talked to some of my colleagues that work in the same area. I was suggested that a very simple model to incorporate the effect of snow should be enough. The simple model goes like this. If snow depth is greater than some value, say x, you can assume the power output to be zero. The value of x reported by prior work varies, but it is generally between 1 to 5 centimeters. I wanted to put this model to a test. I took one site where the snow on a given day was 12 centimeters. I looked at the power and noticed that the site was producing quite high power at different times of the day, which led to the conclusion that snow depth alone cannot describe the effect of snow on solar power output. Then the question became, if snow depth alone cannot predict power output, what are the other factors that dictate the amount of solar power output under snow? We looked into these factors. First, the optical properties of snow determine how much light gets through, and snow depth is just one of the factors defining the optical properties of snow. There are other factors such as flake size, snow density, and snow water content that impact the optical properties as well. The second major factor is that the public snow data that any model will use is generally observed at weather stations that are far away from the solar site. Also, the measurements are done on flat, open surfaces while panels are tilted and maybe under shadows. This makes the snow on panels different than the snow data. All these factors affect the amount of solar power a site generates under snow. So far, we have discussed why snow modeling is important and outlined the factors that potentially determine the power output under snow. In the rest of the talk, I will go through the three key contributions that our paper makes. We look at the publicly available snow data to identify predictive variables. We discuss how to frame the problem of snow effect modeling. And finally, discuss our implementation of the model and some of the evaluations. We analyzed the publicly available snow data from NOHSRC, which is a division of National Weather Service. The dataset reports over 40 variables. Some of them come from the ground observations, while others are based on numerical weather prediction models. After cleaning the data, we were left with 8 snow variables, which are given in this table. The effect of each variable on the optical properties of the snow and ultimately solar output can potentially be modeled when taken one at a time. However, when considered collectively, the variables are simply too many and their interactions with each other are far too complex. As a result, there are no physical models relating all of these variables to the solar output. The problem is further complicated when you consider that the site characteristics make the snow on solar panels significantly different from what is reported at a weather station. Solar panels have low surface friction and which this leads to snow sliding. In this figure, panels with higher tilt almost have almost no snow, while flatter panels are still covered. Also, snow melts very different across sites due to the orientation of panels and shading from nearby objects. We looked at these effect of these variables on power output empirically, and I will quickly take you through our analysis. This graph shows that as the tilt increases, more snow slides and panels produce more power. This graph shows that shading prevents snow from melting and shaded sites generate less energy as a result. So after going through a long list of variables, we have established that the effect of snow on solar output is quite complex and cannot be physically modeled. This complexity makes the problem very well suited for the deep learning approach. However, framing the deep learning approach is non-trivial. There are a lot of questions. Do we build a model for each site? Can a universal model be built? How do we model the effect of other variables such as capacity, tilt, cloud, and temperature? We considered all of these questions while framing the problem. Finally, we decided to decouple the effect of snow from other variables such as cloud, temperature, tilt, and capacity. This was because accurate models for these variables already exist, and we wanted to leverage that prior work. This design decision also allowed us to build a universal model. Please check the paper for more details on local versus global models. In this design, our model takes the output of a solar model which has already incorporated the effect of all the other variables such as site, capacity, cloud, temperature, tilt, and orientation. It then applies the effect of snow as a factor whose value is between 0 and 1. A value of 0 means no power due to snow. 1 means snow has no impact. This model then spits out snow-adjusted power output. To train this model, we use all the variables we have mentioned so far. Also, in the initial slides, I mentioned Department of Energy's SAM model. It uses a simple model for snow, and we use their snow model as a feature to our model as well. Once the model was trained, we evaluated DeepSnow on 10 sites spread across Colorado, Illinois, Massachusetts, Minnesota, and New York. We evaluated the short-term accuracy in predicting instantaneous power and long-term accuracy in estimating annual energy output. We use mean absolute percentage error as the accuracy metric. I would like to point out that lower MAPE means higher accuracy. We use SolarTK and SAM models as a baseline because these are the state-of-the-art solar performance models out there. SolarTK does not model the effect of snow, while SAM uses a model that incorporates the effect of temperature and tilt. We first evaluated the accuracy of different models in predicting annual energy. On the lower end, DeepSnow results in 9% reduction in MAPE relative to SAM. At the higher end, DeepSnow reduces the MAPE by almost 50%. The key takeaway is that DeepSnow does better than SolarTK and SAM model for all the sites. We also evaluated the performance of DeepSnow in estimating instantaneous power output. DeepSnow, as expected, performs significantly better than either of the two baseline models. The previous two results were for the whole year. While DeepSnow outperformed baseline methods, its true impact comes to the light during winter, because during non-winter months, it simply uses the underlying model of SolarTK. Since SolarTK does not model the effect of snow, it has a very high error. So high that it went out of the chart, and I decided not to even show it on the graph. This graph shows comparison of DeepSnow with SAM. DeepSnow reduces the MAPE by 54% at the lower end and 95% at the higher end. This represents a significant improvement over the state of the art. While I have presented just 3 key results, we have evaluated our model in many other ways, and I would like to invite you to look at the paper if you are interested in knowing more about our evaluation approach. In this talk, to conclude, we established a few things. First, modeling the effect of snow on solar output is important. Second, the effect of snow is complex and cannot be physically modeled. Third, the problem is well suited for deep learning. DeepSnow models snow effect using publicly available snow data and prior work on solar performance modeling. Finally, our evaluation show that it does better than the state of the art. Thank you.